everyone, and welcome to the May edition of this webinar series on responsible AI, an in-depth webinar series about the responsible design, development, application, and use of AI. In this series, we will discuss a range of topics related to the ethical, accountable, and sustainable use of AI. By doing so, we want to inform anyone with an interest in responsible AI about tools, methods, best practices, and lessons learned. By sharing this knowledge, we hope to aid you in the achievement of positive societal and environmental impact while meeting commercial or governmental business objectives. Today, we present presentations by Alexander Boer and Mark Roboff. My name is Marieke Peters, and I'm your host for today. I have a background in user-centered design of artificial intelligence, which over time converged into many of the topics nowadays commonly perceived as responsible AI. After 10 years of applied research in academia and at TNO, I moved into business about a year ago, joining Xomnia as an analytics translator. I aim to bridge the gap between academic and applied research and the application domains, business, companies, governmental organizations, all working on the adoption of data and AI. Alexander and Mark, thank you both for being here today. You're not on screen yet, but they will soon appear magically. I will introduce the first speaker, Alexander, and I will introduce Mark at the start of his talk. Alexander Boer is a senior manager of trusted analytics at KPMG, and we got in touch through his colleagues, Mark van Meel and Frank van Praat, who reached out after our first webinar edition, explaining the shared interest in the topic of responsible AI and trusted analytics. So today, Alexander will talk about the role of trust in the use of AI applications, especially in high-risk environments such as finance, the accurate and robust performance of AI systems, where they must be guaranteed. So Alexander will show us how AI and the surrounding organization can be designed and operated in such a way that it safeguards potential risks. Alexander, I leave the stage to you to address our audience.
Thank you, Marieke. So I work at the Trusted Analytics team of KPMG, and before that I have an artificial intelligence background. I used to work as an AI researcher at the University of Amsterdam, and I also lectured. So I gave lectures, for instance, for 2 years about the introduction to artificial intelligence, and that's of course an appropriate topic to start with. What is AI and what is AI risk? Because defining what we are talking about and what risk belongs to AI and what risk doesn't belong to AI is part of our question. The Trusted Analytics team within KPMG, of course, most of you will know that KPMG is one of the big accounting firms in the world. But besides that, we deliver a lot of other services. Part of accounting of the financial statement audit is determining the safety of systems that interface with basically bookkeeping systems or that predict, for instance, financial risk. And we play that role. So we do support the financial audit when they need to know something about an AI component. We also play other roles. So we help organizations in general to deal with strategic choices, with risk and control, and with auditing, etc., related to artificial intelligence applications. As a third function, we also do internal quality assurance for the analytics work that the company itself does. Well, what is AI? I think that one of the most AI used to be a lot broader than it is used in the last few years in the media. There used to be 2 schools of AI. There is a logic or symbolic school, and there is a learning and adaptation school in AI. And I think, well, a fundamental discussion that has been taking place for several decades is basically the cathedral discussion. So if artificial intelligence is directed towards, in the end, replicating all intelligent behavior, then basically we are building a kind of cathedral. And then, of course, you can approach that from 2 different directions. So you can say, okay, so we are building something. So every building block we use, so every brick has to be very reliable. And if that is your main focus, then basically you want a logic-based or functional specification approach to artificial intelligence, because then you know that your foundations are going to be able to carry what you build on top of it. The other approach is basically to replicate what people do, so to build something which is adaptable, etc., or that's basically learning. And that is what is understood as AI in the last few years. So the notion of learning and adaptable systems, machine learning technology, basically. Well, if you look at the, so this is the Cathedral of Boer that you see in front of you. And the Cathedral of Boer basically explains the problem there. So if you would have started building reliable blocks, they would have finished no cathedral. But if you just start building a cathedral, you get what happened there. So only part of the cathedral is built because the ship of the cathedral, well, they basically were not able to build it. The part that they did build has lots of supports that they didn't think about before. And you see that very nicely here on the picture from the outside. And that's basically our issue in this talk. So when we are talking about artificial intelligence, we are usually talking about algorithms, that's another word used in the media, as a model trained with data using a machine learning algorithm. So algorithm in this sense has two meanings. So you have a set of data, you pre-process it, you translate it into training data that can be used for your algorithm. You use that training algorithm to produce a trained model, which is itself also an algorithm. And with that trained model, you can do predictions based on new data that conforms to the patterns of the old data. And this is basically our building brick that we are increasingly in society using to build larger and larger structures with. The problem with AI technology, as we know it now, is basically that the algorithm usually does what a human in its place would do at a task. But if it fails to work, it usually does so in a very different way than humans do. And it is basically the way it makes mistakes that very often gives insights into how it works. So if you look at the first media report, so this was about a line referee that was being followed by an AI camera because the AI camera mistook his bald head for the ball. Now, could this happen to a human being? Well, probably not, because human beings watching the game are usually aware that there are players on the fields, there are referees on the field, and there is a ball on the field. And they also know that the ball, typically speaking, moves independently of the players while their heads stay attached to the players. So in this case, we know what the system has been trained to do, and we also know that basically it was very limited. It only followed the ball, and because the ball at some point crossed with the bald head, it started following the bald head. It's a mistake that human beings would not have made. And we can explain this error basically because the system is doing something that a human being could also do. And that's not always the case. So at the bottom, you see another screenshot from an application which claims to assess personality and job suitability from a 30-second video. This is the kind of thing that human beings cannot do. That also means that we cannot tell whether it is making mistakes, except in very costly ways. For instance, hiring everybody and seeing whether they are suitable or not. And in that case, we really have a big problem. So basically, we have the trained model as a brick, and that brick is very often called a black box. And what we mean when we talk about a black box, basically, it is something which is unexplainable, and the opposite of a black box is something which is transparent. So transparency is opposite of black boxness, and that is one of the things that we are trying to achieve. Now, what is Transparency. There are a number of definitions in the literature, and they all share a certain problem. So an explainable model is one that can be readily presented to the user in some form with visual or textual artifacts. Another definition is, for a model to be fully understood, a human should be able to take the input data and in a reasonable time step through every reasoning step, or in a reasonable time step through every reasoning step required to produce a prediction. Well, we can do that for the football game. We cannot do that for the other application, obviously. And that also is a fundamental limitation to the notion of transparency. Some kind of arguments for transparency preclude any application of artificial intelligence that surpasses our ability on tasks. How does this translate to AI risk? Well, there we also get a bit of a problem, because here we are moving from talking about bricks as part of a wall. What determines the meaning of an algorithm embedded within an environment is basically the process, and not the program artifact itself, nor the data used to create it. So you can think of it in terms of the enabling practices that should make fielding the algorithm possible and safe. And you can think of it in terms of the enabled practice that becomes possible because the algorithm is there. So if you look at the brick basically in a chain of tasks, in a process, you can say, well, there is an upstream direction. So what are the enabling practices that make fielding the algorithm safe? There is a downstream direction of looking. So what is happening with the output of the algorithm? And is what is happening based on the right assumptions, and is it safe? This kind of reasoning is very similar to responsibility in general. So when we talk about human action, we usually evaluate it by the reasons that motivates it. So that's the enabling practice, basically, and what it could reasonably cause, so the enabled practice. And when you compare it to the wall, at the left side, at the bottom, then we also have the upstream and downstream. So upstream is basically what is supporting the brick, downstream is what is supported by the brick. And if you know you are building a cathedral, then of course you want to know that the brick supports what is going to be built on top of it. Well, over the last few years, we have seen a lot of new initiatives to produce legislation relevant to AI risk and AI risk management. But of course, society is mostly worried about the failure of bricks as parts of walls, and not so much about how to look at bricks themselves. But when you are doing an audit, basically, well, you are looking at a brick mostly, right? So part of the solution must be about reliable bricks and not just about practices around it. Well, if we look at the kind of legislation that has been introduced and is being introduced, then we basically see that there are 5 different directions society is trying to control AI from. So the most obvious one, and also a very recent one, is the Artificial Intelligence Act of the European Union. So it specifies which functions are going to be prohibited for AI and which are considered risky for AI. It requires certain risk and control measures for risky AI, and it explicitly addresses the possibility of discrimination. And it creates an exception to collect protected data for measuring bias and from debiasing models. It's going to be there in a few years, and fortunately for us at KPMG, it's going to create an auditing and forensic investigation business for trusted third parties like KPMG. A second direction comes from consumer and competition law, basically. So creating a level playing field in business to business and business to consumer digital marketplaces. And these are the Digital Markets Act and Digital Services Act. What they basically aim to do is to limit abuse of information position and self-preferencing. How is this going to be relevant? Well, it's going to be relevant to trading and recommendation algorithms, and AI is increasingly used there. It only addresses certain kinds of companies, and there is also a time frame of a few years before it will be there. A third one, which is very new, and that also means that the time frame is longer, is that the European Commission or the European Parliament has asked the European Commission to reconsider legal liability for artificial intelligence. So there's probably going to be a proposed legal liability insurance regime for artificial intelligence, which is going to clear up product liability and operator liability for harm caused by AI. And the idea is that it is going to create a compulsory legal liability insurance regime for producers and operators of AI. We don't know yet whether it will be there, because there are some problems, of course, with estimating what premium is reasonable for the risk of AI harm. But that is also going to create basically risk management concerns. And then two, which are already there. Of course, in the financial area, you have artificial intelligence that is used for financial predictions that impact financial statements. That's directly relevant for accountancy. So we basically already do that. Another one, of course, is the GDPR and the Privacy Act. It specifies that all automated decision making should be transparent, explainable, and contestable. And well, that's also already now a concern, and automated decision making that, of course, covers artificial intelligence. When we look at all the kinds of risks that have to be covered, then basically you can think of those in terms of 5 major control directives that you have as an organization working with artificial intelligence. And those are our 5 anchors of trust: reliability, explainability, fairness, resilience, and accountability. And that basically, so when you look, for instance, at the financial statement audit, when you are making financial predictions and they end up in the financial statement, well, that system should be reliable. It should be resilient. And it should be explainable to the extent that the auditor requires it. But when you look, for instance, at a system that takes decisions about people, and those people are stakeholders in that decision, then the decision mainly needs to be explainable, but for another reason. It needs to be explainable to explain the individual decision that it takes about that stakeholder. So that's the concern that comes from the GDPR. And of course, when you look at the legal liability regime, that is going to be a typical example of accountability. So has the accountability for the algorithm been clearly organized? And of course, auditability is part of that. So when you look, for instance, at price fixing, self-preferencing, etc., in competition law, then auditability to check that the algorithm is not using insider information is also an AI concern. Now, what do we bring when we as KPMG do engagements? Basically, we bring in a method of designing control frameworks. So we start with control objectives. Based on those, we look at the risks that are there. We look at what kinds of properties of the system are there that are going to function as risk drivers, and those risk drivers can then be mitigated by controls, and those controls, of course, have to be supervised, they have to be audited, etc. As a side issue, of course, you can also wonder about how this affects business cases, your cost of control. If you want to know what risk drivers are, so this is a very quick example. So for instance, if the predictions of the AI application cannot be adequately or timely verified by observation to measure performance, that is going to be a clear risk driver for the final product. Now, when we look at the brick itself, then basically there are a number of limited root causes of badly trained models. And they basically all come down to the same thing, and that it is not thinking through one of the main ingredients of a realistic problem conceptualization. So the problem conceptualization is part of a good business case. It's part of a good risk assessment. It's part of a good domain and data understanding, and it is also what drives how you are going to measure your performance when you have fielded the system. It is also going to drive basically the loss function you design for training, so the thing you are trying to teach it, and how you are going to test whether it has learned well enough. Now, basically, when you look at how can you see it when you are only looking at the brick, then basically you can reduce that to two key concepts: inductive bias and underspecification. And we will now quickly go through both one by one. So the first one, inductive bias, well, it's based on the notion that machine learning is always based on the assumption that training, testing, and production data are independent and identically distributed samples taken from the exact same causal mechanism that produced the data. And unless told otherwise, the algorithm is basically free to guess what the causal mechanism is and then to build a trained model from that. If you, as a data scientist, ignore differences between samples, you are very often incorporating inductive biases into your model. And these will manifest in a way which is visible, measurable from the outside, as systematic errors. And they will remain systematic errors basically no matter which algorithm or sampling approach you use, as long as you keep using the same data. Now, this is very often misunderstood by people who do artificial intelligence, and very often in the context of fairness of discrimination, as meaning that trained models only reflect an already existing history of bias. This is not necessarily true, since historical decision makers may not have been making the decision with exactly the same information. They may have had access to relevant information that is not in the data, and they may have had other insights in the underlying causal mechanisms. Now, what is the basic solution? It's basically to understand your data very well, and therefore also researching the processes that created that data. Now, the second kind of thing that you can measure about your brick is underspecification problems. And that's basically how, not properly thinking through your problem conceptualization can manifest itself. So generally in machine learning, we start with some problem from the real world, which has business value, and we try to translate that into a so-called well-defined problem, as mathematicians like to call it, a mathematical abstraction of the problem reduced to data. And the problem of the algorithm is then going to be finding a causal mechanism. And with a good loss function and good test criteria, we can find a good loss function, or we can find a good solution. Now, what is the typical manifestation of underspecification? That is that depending on the algorithm and the sampling methods used, we find many different solutions, so many different causal mechanisms, and each are basically different biases. They manifest as different kinds of systematic errors. And designers of algorithms or designers of trained models are too often happy about seeing big differences between algorithms, because they think, well, there's a clear winner. We are going to field this one, but it is a symptom to worry about. The solution here in general is to specify better what causal mechanisms or systematic errors we don't want to see. So to think about your fault models and monitor for these fault models and devise targeted stress tests for them. So for instance, if we are using a face recognition system to decide who can pass through a door, then if we don't want somebody to be refused all the time, then we need to test for that instead of just looking at our average performance and saying, well, it's doing right 99% of the time. We do have to make a side note with this. Of course, to some extent, underspecification is inescapable. If we exactly understand our problem, we are not going to use AI technology, but we should be critical about applications of AI technology. So basically, this is what it comes down to. So for each of these components, you can say there are clear warning systems. So for instance, in a business case, a messy problem conceptualization without an exit strategy or an unwillingness to cut losses is going to create a problem. If your training and test criteria do not model the real-world business payoff, that is going to be a problem. To take an example of that, if there is a big difference between the kind of errors you make, so for instance with discrimination, if you are stopping people based on face recognition and you care a lot more about stopping people unnecessarily than you care about not stopping people who should have been stopped, then basically you should have made that part of the way you train your system.
I'm going to break in a little bit because of the time. So
I'm starting to become aware of that. Of course, forgetting about individual fairness or forgetting about group fairness is another typical one. So this is the discrimination part. So if you care about equal performance for different groups, then of course test whether you get equal performance for different groups. And then finding solutions based on a causal understanding of the domain that conflicts with your common sense is another one. And that's one we sometimes find. So for instance, in an application I saw that was doing fraud detection. So if you are training with all the parameters you have from your training set and you discover that your best predictive parameter, for instance, is the treatment length of the case, then you might wonder, was this treated after it was recognized as fraud detection? Because, well, in the example case that we found, basically they were training a time machine. They were training a system that was predicting whether something was fraud by how long the case had been open. And of course, that information is not actually going to be there in the production setting. So basically, they were getting the causes and the effects wrong. And that kind of ordering effects are very important. So basically, so this is my final conclusion. What we do is to reconceptualize the bricks. So don't only think about the trick model. So this is only your prediction, but think about the way you do tasks as a skilled and well-informed and motivated human. So think about organizing your modeling phase, your prediction phase. Think about decision-making and the payoffs of the different outcomes, the real business value, how you monitor and how reliable your feedback is, how you are valuing errors, and basically, so what are your fault models? So what are the errors that demand an explanation and that you have to do something with in modeling? And you try to bring that into the organization. And basically, because you cannot do that, you cannot automate all of that. So you either build it into the system, or you teach human beings to do it, or you organize governance structures.
Thank you.
Yeah.
So due to the time limit, I'm going to only pose one brief question that was actually posed by one of your colleagues. And it's how do you think that the AI regulation will impact the costs of control?
That's a very good.
And I'm going to have to ask you to keep it brief because we also want to, Mark, of course, to.
I think there are business sectors where it will not really have an impact on the cost of control because most that is required is there, and it's mostly about skill development. But certainly in mostly online businesses, this could have a huge impact. So things like recommendation algorithms, etc. Everybody is using them, and in a few years, you will have to be transparent about them. People will have rights to ask about stuff. You will have auditors, etc. You are going to be doing a lot.
Thank you. All right. Thank you for your talk, Alexander. It was very interesting, and I have a lot of questions, but unfortunately, no time. So maybe we can talk about that after the webinar. For now, let me continue to introduce Mark Roboff, our second speaker. So I'm gonna get my presenter view here. So our second speaker is Mark Roboff. He recently founded his own company, leaving DXC Technology and now taking on the role of CEO of the Skythread Aero in Irvine, California. Mark and I got in touch through a joint acquaintance, Jeroen Mulder and Astrid Apostolidis at KLM. And they commended Mark for his visionary leadership towards applied AI in aviation. So Mark today will provide us with a talk on risk assessment and management by focusing on simulation-based testing. Mark, I look forward to your talk, so please feel free to grab the mic.
All right, thank you, Marika, and thank you for the opportunity to speak this morning, at least morning my time. Again, my name is Mark Roboff. I have a 15-year background in AI and analytics and related technologies. 10 years of that's been dedicated to aerospace and aviation. Half my career has been with larger companies like DXC or IBM, where I was previously the global solution leader for aerospace and defense at IBM. The other half of my career has been with startups. I was at a small AI startup several years ago, funded primarily by Boeing. And now I am at a startup of my own. But what I've come to talk about is not my professional work or anything that my company is doing, but a standards development initiative that is taking place in the aerospace industry right now around the certification of AI. So in addition to my professional career, I chair as a volunteer activity the industry's largest standards development effort to find a way to develop what we call a means of compliance for the certification of AI and machine learning and safety critical systems. So I'll unpack what that means, and I'll take you through what we're doing and some considerations. So Alexander did a very good job, I thought, of describing what AI is, and gave us a very good view of how to think about it and how to think of the concerns that come up in building and managing AI systems. I'll add to that a little bit with a classification of my own. So when I look at AI from a practical perspective, not really talking about how it works or what it's made of intrinsically, but how it's used, I'll argue that AI systems, AI applications fall, generally speaking, into one of two camps. One is AI that analyzes or predicts stuff. So when we think about AI as it's used in societal applications, and when we think about the type of AI that is now being addressed with new European Union proposed legislation, it's AI of an analytics nature that most addresses. So think of AI algorithms that might do credit cards, credit score reporting, or AI algorithms that may predict retail habits, or that may try to catch nefarious or criminal individuals in CCTV. There's another, of course, class of AI that operates things, controls things. When we think about, for instance, self-driving cars or something like a Tesla autopilot, that is an AI that is built with some fundamental differences than the type of AI that might be used in an analytics application. And that's the type of AI that we're concerned with in aviation primarily. How do we build machine learning systems that can provide autonomous functionality across the airspace system, both from operating planes, could be the typical airliners that we fly today. It could be new types of aircraft that the industry has been working on over the last decade, something more akin to an air taxi, an electric helicopter, if you will. Or it could be leveraging AI to manage the airspace. So imagine Today, air traffic control is still very much a manual and human-powered endeavor. In the future, we can imagine AI managing air traffic control. So these are obviously, sort of end state ideas, right? Pilotless aircraft, a computerized, completely automated control tower at the airport. In reality, what we see over the next 15 years is AI merging into these type of applications in degrees, and also merging into a lot of the supporting applications that humans work with to either fly an airplane or manage the airspace. So for instance, it would be leveraging AI as an alert system, or as a recommendation system, or as an assistant, right? That would take workload off of the air traffic controller. Something that's very important, because if we imagine a proliferation of drones and air taxis, something that we in the industry call urban air mobility, or now more commonly advanced air mobility, one of the things that the global community has been concerned about is, well, right, we have a complex airspace to manage already, but now if we're going to add 10,000 new vehicles over the skies of, say, London or Los Angeles, how do we deal with that? Is that too much air traffic for a few humans to manage in a control center? So how does AI come in and assist? Similarly, in the cockpit on an airplane or airliner, how does AI improve the systems that a pilot uses today? How does AI improve navigation, turbulence detection, detect and avoid systems, for instance, to how does AI begin to take over function? And again, just on the air traffic control side, how does AI begin to shift the workload, producing a safer aviation industry? How do we maybe go from 2 pilots in an aircraft to maybe 1 pilot in an aircraft with AI assistance? And then ultimately, of course, how do we enable fully autonomous systems, and why? I'll talk a little bit about why we might want to do that as well. So that's the type of AI that we're concerned with here. It's more AI for autonomy. It's more AI that takes an operational or executive decision-making function as its core application capability, versus something that's going to do an analysis or a prediction. So then the next thing I'll say that again unpacks what this is all about is that I think folks who know a little bit about aviation probably know this. When you look across all modes of transportation, one thing that is commonly said about aviation is that it's very highly regulated, right? So the bar of safety and safety assurance in aviation is much higher than the bar of, say, safety and safety assurance in automotive, or maybe even in rail travel and in other modes of transportation. When we hear about a plane crash, it's a national or international news story. Several plane crashes become a crisis that that could take years and years to resolve, as we've seen, for instance, with Boeing 737 MAX, right? We say and we know that aviation is amongst the safest modes of transportation, right? But that didn't come naturally, and that's large part due to how highly regulated the aviation ecosystem is. So we can't today just go and build a AI into our aircraft the way we see car manufacturers like Tesla or GM building AI into their cars. There are existing methodologies, both from a software and systems development process and from an assurance process, as well as how one would demonstrate that assurance, that must be followed if you're building an aircraft or a system on an aircraft and want that aircraft to get certified by regulators like the FAA in the United States or EASA in Europe. And those existing methodologies are simply incompatible with how artificial intelligence and machine learning works. And it comes down to principally what Alexander said in terms of black boxes, right? So traditional programming is a logical composition of an idea, right? I have a system I'm building. I define the requirements of that system, and then I go and code against those requirements. And in building a complex software system, like an autopilot system, for instance, or a fly-by-wire system on an airplane, what I have to do in order to get that system certified is demonstrate to the regulator how every single line of code I write logically connects to and implements my performance requirements, my robustness requirements, my safety requirements, etc. And of course, in machine learning, we're not coding, right? We're gathering some data, giving it to an algorithm on a computer and say, here, you figure out what we're supposed to be doing. Right, and because of the way machine learning and principally neural networks, the way those systems work, we can't logically connect the inner workings of a neural network and say, well, it's because of how this neural network has constructed output from my input that we know that we're implementing the requirements. We need a different mechanism. So that's what my committee is designed to do. It's designed to create that mechanism, that new means of compliance. So that the industry has a way to certify AI and ML systems, and if we can do that, then there'll be some very, very interesting things that we'll be able to build, and will also fundamentally change the way that aerospace systems and airplane systems are developed, without necessarily at all compromising the safety bars that we've achieved, while also, I would argue, dramatically improving safety down the line. So we'll talk about a little bit, what this works like. So the committee that's working on this, I'll just talk about very, very briefly for anyone that might be interested. It's sponsored by actually two standard development organizations and functions as a joint international committee. One based in the United States is SAE International, right? And the committee under SAE is called G34. And then it has a partnership with EuroK, which is a European-based standards development organization for aviation. And G34 is partnered with a counterpart within the EuroK organization called Working Group 114. So the name of this organization that's trying to figure out how to certify artificial intelligence machine learning for aviation is called G34 / Working Group 114. It's 500 people. It's engineers and technical fellows and certification engineers and data scientists and research fellows from Boeing and Airbus and all the engine makers and all the avionics suppliers. Essentially, we have the full scope of the aerospace manufacturing base and engineering base and supply chain working with us. We also have a number of airlines. KLM is very much engaged. We have folks from Lufthansa, even a couple pilots, folks from the cargo carriers in the United States. We also have some IT hardware providers. Intel, NVIDIA has been very engaged. Defense companies like Lockheed Martin and BAE. Also research labs from various military institutions, and of course NASA. Most critically, we have great support from the global regulatory community, ICAO at the international level, EASA in Europe, the FAA in the United States, Transport Canada up in Canada, ANAC in Brazil. Those are the regulators that are commonly known as the Big Four. That set guidance and policy for the entire world, more or less. And what we're doing is we're working on a standard that is going to be produced in the fall of 2022. And then from there'll be future versions of the standard that address more and more complex topics as AI and ML mature in aerospace and aviation. So the standard that we're producing is built, or I should say is written, it's developed in conjunction with a number of key guidance papers that have been released by industry leaders over the last 2 years. Most critically, EASA has released something called the AI Roadmap, which is actually, it's a very easy read, and it's a very compelling read. The AI Roadmap was released in January of last year, and it talks about essentially what needs to be solved in order for us to have a means to demonstrate that a system that incorporates machine learning is as safe as a system that doesn't. And assuming we define these criteria, which are actually listed here on the left, it's how do we assure the data that we gather to build a neural network is as representative as necessary of both the environment, the physics, and the systems of what we're trying to model, so that it can stand in as a facsimile for real life. Call that data assurance. What are the methodology? What are the performance requirements of our machine learning methodology, of the data management methodology, of the verification validation methodology? Those are other things that we're working to determine right now. Very important in aerospace engineering is this concept of V&V, validation and verification, or verification and validation, although it's less common because in a process diagram, validation usually comes first. And that's really around how we go and organize work around safety assurance. It's understanding how we craft robust requirements, how we assign robust requirements to systems development and track that, and then how do we test the system we build against the requirements? How do we know we've built a good system? These are things that we're working on right now that will be produced in that first standard. And then as we progress over the decade and into the 2030s, what we'll ultimately be doing is addressing the entire architecture for certification. And we'll talk a little bit about that. And we have a long-term vision of what certifying AI may look like. Right. So again, we talked a little bit about that timeline, and even before, I'll mention, even before that standard is out, what this group has already done right now and is available to go on and download and read is a gap analysis, supposing what we would think of as a fully elemental AI ML development workflow, and assessing that workflow against existing standards so that we know where the gaps are. We know exactly what we need to solve for, right? And again, it comes down to principally this misalignment between AI and the black boxes, and the fact that there's this problem of explainability, with the fact that at the end of the day, existing development standards in aviation require complete line-by-line traceability. So, skipping ahead a little bit, what I want to talk about is, again, this long-term vision. At the end of the day, right, we understand that regulators, they'll certify an engineered product like an airplane, right, differently than they certify people to fly that airplane. And what we see as a long-term vision is a merging of those two principles. How do we take a black box that we can't necessarily deconstruct and define trust and communicate trust in that black box? Well, we can look at the human brain, and we can understand that the human brain is a black box. And in that, right, we recognize, right, we have a way to assess and certify our trust in human pilots. We could take that architecture and apply it to AI. Think of virtual ground schools. That aligns very well with what we talked about in data assurance. Think about a check ride, the test that we have that allows regulators to say this pilot, has learned its material, knows how to fly its airplane. That, right, we can create a virtual version of, and that's what comes down to, again, simulation. So today, right, we test the proficiency of our human operators in the real world, in real time. A check ride lasts about an hour, right? If we can create a digital facsimile of that, right, something that correctly and fully models the real world environment, the flight models, the aircraft systems, and does so to a degree where we can assess something virtually and say that it's going to perform equivalently in a physical environment, then we can create a virtual environment to do virtual check rides. And when we can do virtual check rides, instead of tests taking an hour, where you can only cover so many different things, you can have tests that run in a fraction of a second that can test for orders of magnitude more cases and edge cases and scenarios. It's a concept to see how we can build safer, more performant systems than what we can do today in the physical world. Right. I know we want to have some time for Q&A, so I'll very quickly skip over this and end. There's a whole architecture that will be coming together over, again, the next decade that will ultimately create a framework for this. How do we leverage flight simulators? Again, right, the coming together of model-based engineering, very digitally accurate digital twin representations of the real world, of flight models, physics models, flight systems, to create this environment where simulation can replace test flights and that simulation can replace check rides. The end result is that today, building an aerospace system, training a pilot, right, it takes an exorbitant amount of money to do so. Building an airplane today, or even just a complex aerospace system, can take hundreds of millions of dollars. There's a lot of ingenuity and innovation happening right now in aerospace, but there's a huge barrier to being able to build a successful program. And that has lots to do with the amount of physical flight tests that are needed today to get something certified. If we can move the physical world into the virtual, we can shrink that cost down and lower the barrier to entry. If we can bring virtual check rides to the operational side of aviation and begin to build AI systems that can interface with pilots, we can improve reaction time. We can look across a litany of incidents that have happened in aerospace over the last 10 years. And if we look at how pilots reacted and the sequence in which pilots reacted and said, well, if we were able to shrink that to mere microseconds, right, most of these incidents could be avoided. Right. And that's what the holy grail of this is all about. It's merging the executive decision making of humans with the speed of computation. There's something in aviation we call the OODA loop, which is about how aviators assess and execute, right, their flying decisions. And what AI will allow us to do is shrink that OODA loop, building a safer system. So I know we only have maybe a few minutes for questions, but I'll pause here.
Thank you, Mark, for this talk. It was a lot to cover, and I think you did a great job in covering it. So I'm going to take a look at the comment section to see whether there are any questions. Again, Mark van Meel posed a question, and his question is that of problem under specification. So do you see any potential pitfalls in testing models by other models?
And testing models by other models. So I mean that's something that the community is working on. They're different, they're different approaches, different schemes in terms of how these systems are going to be built. What we're looking at necessarily is not prescribing what approaches, what models to use, but to specify performance requirements, right? And to understand in specifying those performance requirements, right, what are the likely scenarios in which the aerospace community will be able to meet them, right, and at what cost factor.
Yeah, I think that may be the underlying question, but I cannot check with Mark, unfortunately, due to the way that we now do this online. But of course, a simulation in itself is also a model. So somehow your testing capability is only as good as your simulation. So how do you then verify that your simulation is realistic enough to cover for all the potential scenarios or situations that you might come across in reality.
So when we talk about simulation, when we talk about flight simulation, there already are an existing set of well-established requirements that specify, at least for humans that train on flight simulation, what's required for facsimile level performance, right? So the idea is that we extend what's already common practice, right? And layer in on top, right, AI systems. And part of what we're trying to figure out right now is there a gap that needs to be solved in terms of response time that needs to be looked at. But today already, right, we have very accurate physics-based models that are used for elements of training, elements of check rides and of certification. We have models that actually bring in not a simulation of software, but the actual software. So you think of an Airbus airplane, which famously has a fly-by-wire control system, right? Imagine being able to take that control system and put it in a fly-by-wire, put it in a flight simulator. It's fly-by-wire.exe. That's done today. So we're already at a very high level of fidelity. And now it's about just assessing what gaps need to be closed.
Yeah, I was also thinking the same thing while you were giving your talk. Like,
I think something may be frozen.
we're back.
There you go. You're back.
There's also the addition of it being highly regulated. So you have physics controlling the airplane. You have a lot of technology that is producing a lot of data and that is being reproducible. It's highly procedural. It's highly regulated. Mm-hmm. So that makes this, of course, a very suitable domain for this kind of solution, I think.
It does, right? Because one thing that I think a lot of when we think about AI philosophically, and when we think about AI in terms of sort of the hard problems, a lot of it is around interface, right? What are your boundaries around inputs and outputs? And working in a highly regulated environment, and working in especially a very rigorously engineered environment, those interfaces are well defined.
Yes, thank you, Mark. I think we're going to go to the closing, but I very much enjoyed your talk.
Thank you.
Fritz, can you put my... Yes, thank you. So for the upcoming webinars, in June, we have another webinar that is about pair AI and explainable AI. So Hilde Weerts and Jasper van der Waa will each give a talk about each of these topics. I would highly recommend, of course, for you to all be there. And the same goes for our July edition, where we invited Paulus Achterberg to talk about platform economy and systems thinking. And she will talk a little bit about the future of platform economy and the challenges that might introduce and how you can solve it through systems thinking and regulation. And in addition to that, we will also have a speaker who will talk about the topic of EU AI regulation. So the new proposal for AI regulation that is currently under review at the European Committee, and what that might mean or imply for the future. So if you have any questions about this webinar, or if you would like to get in touch with us about responsible AI, then please feel free to get in touch with Annemieke. She's our Chief Commercial Officer, and she's always open for questions or just to have a chat with you guys. So hope to see you again on June 10th at 4 p.m. See you then.